So if I'm fixated there, I can see the T, but it doesn't mean that I will report the T. What we know from a lot of work on visual attention is that your covert attention, when you're fixating for a quarter or a third of a second, your covert attention is probably bouncing around to visit 4, 5, 6 items. And then after a quarter of a second or so, you redeploy your eyes someplace else. In this case, in this cartoon, though you could have seen the T, you didn't happen to pay attention to it. And if you don't happen to pay attention to it, you're not going to report it. Though you will be perfectly introspectively convinced that you looked at that part of the image. We can put some numbers on this. So in this kind of experiment where you're looking for a T among L's, let's say if you're fixated at one point that is some distance in degrees of visual angle, 360 degrees around your head. 1 degree is about your thumb at arm's length. Useful field of view is often heuristically estimated at about 5 degrees, though that's a quite arbitrary number. But in any case, we can measure how far your eyes are from the target and ask, what's the chance that your next fixation is going to go to that target in an experiment where your job is to click on the target, so you're almost undoubtedly going to fixate on it. And here's the data for this task where you're looking for T's among L's. On the y-axis, what you've got is the proportion of the next eye movement that go to the targets, and you'll see that it's well less than 100%, even when the eyes are within a degree or two of the target. So your eyes can be very close to the target, and if you don't happen to get your attention on it, you simply will not report it, at least not after that fixation. We've done the same thing with the radiologists looking at mammograms, and we can let's expand our criterion a little and say, what's the chance that any of the next 3 saccades go to the target? Because we know that targeting saccades sometimes miss and you have to make a correction, or maybe you only saw the thing just before you moved to a weird location and you have to jump back. So next 3 targets, this is radiologists, and you see basically the same kind of data. Even when your eyes are within 1 degree of a clearly visible finding, something that would totally show up as retrospectively visible when you ended up in court, there's a very comfortable chance that you won't find it after that fixation. Now, the reason people don't miss 40–50% of findings on mammograms is that you're going to pick it up on a subsequent fixation of some sort. But the point here is that simply putting your eyes near the target is not enough to allow you to find the target. We can illustrate that with, this is definitely not a radiological image, though it's a nice image. Let's build up a little theory of what we're saying about what you're seeing. The claim here is that at any given moment, you are paying attention to one object, you get something that we can call the gist, the unattended or pre-attentive gist of the image, and you've got a theory at any given time of what you're doing. I'm looking at a Giotto fresco right now before I was looking at a mammogram, that kind of a theory. But the claim here is that you won't detect a change in this image unless you happen to be specifically attending to the right thing. So what I'm going to do is I'm going to alternate back and forth between 2 versions of this image. Oh, it might work if you want, here's the image flickering back and forth. in a crowd of 789 people, somebody has noticed the change. If you notice the change, you can type it into the chat box. Anybody who I can see notice the change yet? No. There you go. Look at all those people putting it in there. Now, the reason I'm alternating, changing the orientation somewhat is to mask the low-level luminance transients that would otherwise immediately tell you where the change was. So here, let's do the same two images without the change in orientation. And you can see that's a pretty trivial change. And I wasn't messing around with you. It's there here too. The point is that if you weren't attending to the right angel, even though that was happening very literally right in front of your eyes, and you might have been sitting on the neighboring angel, in fact, you simply don't see it in a way that allows you to report it. This also makes the point that it would be really lovely if this year's mammogram and last year's mammogram were perfectly aligned, because then you could do this to see what's going on. But as you will guess, you cannot. The alignment of any two mammograms is not adequate to do that. Though there's an interesting story to tell about toggling between two mammograms, which we can talk about some other time. All right, so why do you need to attend to one item at a time? That seems like a pretty severe limitation, and obviously leads you to miss inconvenient things like vanishing angels. Let's talk a little bit about the basic science of attention to shed some light on this. So here's a piece of a Where's Waldo image, or if I'm in the UK, it's Where's Wally, right? You know, anyway, same guy. You won't find him, he's not present in this little segment, but we can ask what you see. And I can ask you now, was there a lion there? You may or may not have noticed there was a lion. Now you can perfectly well find the lion. It's not difficult. And that immediately gives us some insight into what's going on here. First of all, it tells you that search is necessary. If the search wasn't necessary, the Hanford, the guy who draws these, wouldn't have made a fortune drawing them. It would have been just, there's Wally, and that would have been a bit of a bore. What was there if you didn't see the lion, or what was there before you found that lion? Clearly there was something there, and that's the problem of what's known as pre-attentive vision. Before you get your attention onto the object, you are seeing something. What is that something? You can also talk about what happens when your attention moves off, say, from the lion to the bus, and ask, does that remain lion in some meaningful sense? That's the problem of post-attentive vision, which we won't talk about much today. Here we'll talk about pre-attentive vision. Pre-attentive vision is a term that goes back to the 1960s. The ideas go back at least to the French philosopher Condillac in the 18th century. And he talked about going to a chateau and at night and in the morning, flinging open the curtains and asking, what's the first thing you see? And he said that you wouldn't immediately see cows and hills and towers. You would see little patches of color and shape, he thought. So here's my chateau and its curtains. I will fling the curtains open, and we can use the chat again if you want. We can fling the curtains open and you can tell me what you see. We don't need the poll this instant, Ian, 1 second, because first I will tell you what your answers are. Oh, well, and that, how nice, people are putting the right answers in. So you saw some pluses, you saw some X's, as people are saying, they're reporting the colors. People report all the right colors, red, green, blue, and yellow. The critical question, and this is what we need the poll for, Ian, is which of those pluses did you see? So if you can, there we go, the poll is up. Let's see what we get for an answer. Actually, I usually find that this is a little like the Kundell taxonomy, if you were to guess that the answers were evenly distributed, you would not be far off. But what do we have, Ian, for answers to this? An honest crowd that gives a 33% plurality win to no idea. And that's the point. You can close that, and I need to click there again. Here's what you actually saw. The correct answer was both. There are some with red vertical and some with green horizontal. And what's interesting here, and what tells you about why you need attention, is that before attention arrives, this object is red and green and vertical and horizontal, and this object is red and green and vertical and horizontal. And it's only once you attend that you can do what's known in our trade as binding the features to the object, which allows you to recognize the specific object, because you need to understand how the features go together. You may know that there are features there, but you don't know how they go together until you get your attention on them. We can illustrate that with another demo. In the next slide, what I want you to look for is the plus that has the red vertical and green horizontals, all right? And this isn't gonna flash, it'll stay there. You have all the time you need. So that's the guy you're looking for. Ready, there you go. You're saying to yourself, I'm good, I found that one. And now you're saying to you, well, there's kind of a lot of them actually. And now you're noticing that half the display is that. And if you're particularly astute today, you picked up that one over there. The point here is that as soon as the image came on the screen, you knew red and green pluses everywhere. But only once you start deploying this selective attention from item to item did you know which red and green plus was there. Now, in the normal world, you're not quite so impaired, because the world isn't made up of things, all of which have exactly the same set of features. This is for demo land. But you can see that in order to recognize an object, what you're going to need to do is to get your attention onto that object. So we see something everywhere. We see more near fixation, and that gives us this idea of a useful field of view. But then to recognize, we're going to need to bind features, and that's going to require attention. So let's now switch back to radiology, and we'll switch from breast to lung in this case. So if you're off getting screened for lung cancer these days, you'd probably be getting a CT, not just a simple 2D X-ray. And we were curious about how people searched for lung nodules in a 3D volume of image data, right? We knew quite a lot about how you search in a 2D image, but really there wasn't much known about search in a 3D volume of data where you can move through the data. And this is work done with Traft and Drew, now a professor at University of Utah. Well, actually now sitting in Frankfurt on leave. Here's what the raw data look like. What you're looking at here, these red dots are plotted every millisecond as the radiologist looks for lung nodules, and so the radiologist is scrolling around through the stack of images, starting in the lower right here, jumps up to the upper quadrant. You'll see jumps over to the lower left in a second here, and so on. And so we can collect a pile of data of this sort. Now, how shall we look at it? A little tricky to look at the data in 3D. So what we'll do is we'll very coarsely code the 2D XY plane in color. And now what I'll do is I will plot the time on task on the x-axis and depth, the slice through the lung on the y-axis, and the colors will show you roughly where they are in the XY plane. And you can see that this radiologist, looking at this particular image, sat in the blue quadrant, went all the way through the depth of the lung, came back, moved to the red quadrant, went all the way through the depth of the lung, and so on. That's not the only way to do this task. It turns out that people fall into two different categories when we looked at their data. And here's the other method. Here you can see another radiologist looking at the same lung, going through it only once. But if you see how the colors are jumping around, what you can see is that this radiologist is moving all over the place in the XY plane while moving much more slowly in Z, in depth. And we've dubbed these two categories of strategies as drillers, the people who sit at one location in XY and drill through the depth of the lung, and scanners who move more slowly in depth, but scan all over in XY. The obvious sort of question here is, well, what should you be teaching your students? Which one is better? We don't know. We're underpowered, a chronic problem in medical image perception, because it's really hard to get enough data from radiologists to answer these questions. Hence my my hope of persuading some of you to be volunteer observers in these sorts of studies. But the hint is that drilling may be better. The other hint that was interesting in this data set is that scanning, there may be an age difference, that the scanners may have been the older radiologists who learned in the film era, and that the drillers were the digital native sorts who had learned once scrolling through stacks was simply the way you did it, rather than having a whole collection of even CT images spread out over a light box. All right, meantime, back in the lung in this experiment, we've got these radiologists looking around for little white nodules. And on the last case in this study, we did something a little odd. We stuck a gorilla in the lung. It's a little easier to see if I fiddle the contrast here. We stuck a gorilla in the lung. The radiologists were instructed to basically do the task the way you would do it in the clinic. And 20 of our 24 radiologists did not report out seeing a gorilla. First important point to make about this, particularly with this particular audience, this is not a criticism of radiologists in any way, shape, or form, not of radiologists as a group or of the 24 we tested. What this is part of a substantial body of evidence that says becoming an expert radiologist makes you an expert at using the human search engine for a specific set of tasks. It doesn't grow you a new visual system of any variety. There've been a variety of studies to look at whether or not expert radiologists are better at other visual puzzles, for instance, and there simply isn't data supporting that. What you have become, to become a really competent radiologist, is really good at using the basic human search engine to do a novel task. Many of you may know why we used a gorilla, but let me just tell those who don't. There's a famous experiment in my trade where non-experts are being asked, look at this little ball game and count the number of times the white shirts touch the ball. And as you can see, in the middle of this video, a woman in a gorilla suit walks through, pounds on her chest, and wanders out. And then after the fact, you say, okay, how many times did you touch, they touch the ball, and they say 12, and you say, great. Did you see anything else? Saw elevators. Did you see a gorilla? What are you talking about? And then you can show them the video again. And of course, everybody can see the gorilla in absolutely the same way that everybody, we did all the relevant control experiments, everybody can see this gorilla. There's nothing subtle about this gorilla. It's just not being reported out. Why does this happen? An important attentional factor here is what we call guidance. The radiologists have in mind that they are looking for something small, white, and round. That biases them against finding things that are big, black, and shaggy. And we can illustrate that here. Let's go back to T's and L's. Look for a red T in this display. You'll find it relatively quickly. That's not a problem. The interesting point here is you should have the clear introspection, the correct introspection in this case, that while you did not immediately know where the T is, you knew you did not need to pay attention to black things. You paid attention to the red things that were going to be your target, and that helped you out in this particular case. Here, to show that there's more to this idea of guidance than just something like color, let's do this in a scene. This is a demo put together to talk about medical image perception to a crowd that are not radiologists, who wouldn't know a lung nodule if it bit them. So, you know, small, white, and round. Okay, that sounds like golf balls. Look for golf balls in this image. Okay, so how'd you do? You found that one. Probably found that one, even though it's atypically green. Odds are you did not find those 5. And odds are that you did not find this one, even though it's higher contrast, more salient than any other golf ball on that image. What went wrong? What went wrong here is what we call scene guidance. You understand this scene. You know where golf balls should be in a scene like this. And as a result, you did not guide your attention to the trees where golf balls have no business being. Even if you happened to let your eyes flick over it, you would have committed a recognition error. You simply would not have noticed that those were real golf balls. Oh, by the way, in our gorilla experiment, radiologists on average, their eyes landed on the gorilla for about a second. They got their eyes there. They just didn't see the gorilla somehow. But you can see how this is part of the answer to the question of why the readers, with this image I showed you before, didn't look in large parts of the image. The answer is they knew immediately that if there was something, that there might be something in this image. They obviously scrutinized parts of the image extensively, but they knew where there would not be anything in this image. Scene guidance is normally a good thing, right? If you're being driven in a taxi cab somewhere down the highway and the driver says, "I'm looking for the exit sign. I wonder if it's on the seat next to me," or something like that. You don't want to be in that taxi cab. You want to be in the cab where the guy knows where exit signs are supposed to be. And you want to be the radiologist who knows where findings are likely to be found, because otherwise you're going to waste huge amounts of time. If you end up in a lecture like this, you'll miss some golf balls, but normally this is okay. This is the gorilla is an interesting example because in a sense, it's an incidental finding that was clearly missed. And missing incidental findings is a known problem in the trade. Now, you may say, and indeed a number of radiologists have said to us, that's not fair. Gorillas simply never happened in the lung. Can't tell you about it today, but we have worked on this problem too. It's not just gorillas. the things that are not the immediate object of search are systematically more difficult to find than the items that you have clearly in mind. So you don't attend to everything that's inside this useful field of view, and guidance, in some cases, guidance very useful, but in some cases it may steer you away from things that you might otherwise want to find. Looking at the time, let me tell you one more factor that contributes to this how you miss what's right in front of your eyes problem, and that's the problem of prevalence. Radiologists, particularly in screening situations, are looking for targets that are very rare. Also true at the airport. You don't want to get on a plane if there are guns and knives in half the bags being checked through that checkpoint. Actually, I'll show you an example here from security type stimuli, because that's where we started with this one. Here's a radiology task where the readers get a whole heck of a lot less respect than you guys get. And they're doing a very difficult task. So be nice to them when you go back to flying. So you're looking for a threat. Threats are rare. That's a knife. That's about as easy a target as you can get. When we did this in the lab, we did knives and guns. We didn't do bombs because they're just too difficult for novices. But we did an experiment where you say, okay, let's take these 20 bags that have guns and knives in them, and we'll either embed them in a stack of 40 bags, where there'll be targets on basically every 50% of the cases, or in 1,000 bags where only 2% have targets, but same threats. These data are from novices, not from airport security personnel, because if I was showing you real airport security data, I can't put a real error rate on the y-axis. It's security sensitive information, and I promised I wouldn't. But with these stimuli, with novice subjects at high prevalence, they missed 20% of our guns and knives. Same threats at low prevalence, they missed twice as many of them. If you ask about false positives, the effect goes the other direction. But if you ask which kind of error you want to minimize at the airport, a false positive means your bag gets open. A false negative means that there's a gun that got onto the airplane. So clear, big prevalence effect. Okay, that's nice. Would it ever happen in a clinical setting? So we did this at our hospital by sliding cases into the workflow. The real power behind this study is Carla Evans, who's now faculty at York in the UK. There may be people on this call who know her. And the key result here is you get the same result. If you look at the miss errors at high prevalence, when these clinicians came to our lab and looked at a bunch of cases at where cancer was present on half the cases, they happened to miss 12% in this particular set of images. The same images in the regular workflow, when they thought they were doing their regular job, they missed 30% of those cancers, purely because they're rarer. And this also happens at the airport. Now you can't figure out what's going on the y-axis. That's on purpose, but you can see that those green dots at high prevalence are doing something different than the low prevalence. And I'm telling you, that's the same effect. So there are three important aspects of attention here. This idea of selective attention, the idea of guidance, and these prevalence effects, all of which can conspire to cause you to make false negative errors, and all of which are worth thinking about if you're trying to think about what kind of interventions might make errors less common. But I did promise to wrap things up by telling you a happier story, because if you're sitting there saying, oh my God, it's just inevitable that I'm going to miss things, and I'm just going to go home and cry now. Let me give you one piece of interesting, what you might consider to be good news. And that goes back to this idea of gist. Let me show you a non-radiology example. What I'm going to do is flash a string of images at on the screen here for about 1/4 of a second each. And your job is to notice when you see the chimpanzee. So on your mark, get set, go. Whoops, on your mark, get set. Why did it go there? You are going to run, aren't you? There we go. Right? Did you see a chimp? No, let's try it again. It's a little, this one's a little dicey over the internet because sometimes the timing is such that the image literally doesn't show up, but we'll try it one more time. Yeah, okay, Daniel found it, we're good. So whether or not you saw the chimp, what's actually interesting here is that as each of those images was up there for 1/4 of a second, you knew the gist of that image. I'm looking at a forest, I'm looking at a beach, I'm looking at a street. You get that sort of information from across the whole image very rapidly, much too rapidly for you to be going and selecting and binding enough objects to do it. It's more like a texture that you're appreciating. And this was interesting to us because when we sit down and talk to radiologists about how they do their job, and this holds in other areas of expertise too, you often get the report, oh, you know, when that image first came up on the screen, I knew there was something there. I couldn't tell you where it was yet, but I just had this feeling. Now, that could have just been selective reporting after the fact, but it could be a real thing, so let's find out. So here we did a sort of an odd experiment. We flashed a mammogram for 1/4 of a second, and we said, we know this isn't the way you do it in clinical practice, but would you call her back? Give us a rating of whether you'd call her back. The folks doing this one are a couple of postdocs and a couple of radiologists, but again, led by Carla Evans, who still is at York. So here's how we're going to look at these data. This is a classic receiver operating characteristic graph, ROC curve, false alarm or false positives on the x-axis, hits, true positives on the y-axis. If you're perfect, you're in the upper left. If you're guessing, you're on that main diagonal. And the important point is that with the images flashed, radiologists clearly are not guessing. When you run this on novices like me, we're sitting smack on that black diagonal line. We're guessing. But if you're an expert who reads mammo, and the more mammo you read, the better you do at this, unsurprisingly, you can beat chance in 1/4 of a second at saying whether or not this is an abnormal breast. Again, nobody's suggesting that this is a great way to do mammo. If you're an expert radiologist, your real data lie closer to that perfect upper left corner in that sort of pink square. Are they just estimating breast density? No, it turns out that this measure is uncorrelated with breast density. Are they just looking for a violation of symmetry? Well, that's interesting. Why don't we just show one breast rather than the pairs of breasts we showed initially? And the cool thing about that is now we can separate out the data for the breast that has the lesion in it and the breast contralateral to the lesion. So for the breast with the lesion, we get the same result out again. So its symmetry is not the driving factor. But what's really interesting here is they can still beat chance in the contralateral breast, the breast that doesn't actually have any focal sign of cancer in it. Well, that's cool. If you can do that, how about if we go and look at the priors? So we can go 3 years back and ask, do you think this woman will develop cancer within the next 3 years based on a quarter of a second look at the image? And it's not a huge signal, but there is evidence that radiologists can beat chance at that. That's a sufficiently surprising result that you'd like to replicate it. So let's go from the US to Australia. The relevant line on this graph is the purple one, and you can see that, again, expert radiologists can comfortably beat chance, telling you whether or not this image comes from a woman who will develop cancer, but at the moment, is entirely properly considered to be normal. So is there a gist of breast cancer? There does seem to be some sort of a signal there. And Carla in particular is now working on the question of whether or not this could be an unexploited imaging biomarker. You're never going to, you're not going to diagnose on the basis of this, but what you might say is if you've got that signal, this is a patient who should be seen every year, not every 2 or 3 years maybe. And if you don't have the signal, maybe you can go a little longer. We don't know, but that's an unanticipated superpower that you've developed that we didn't know about before. So what did I tell you? I hope I've shown you that there are limits on the human search engine that guarantee that you're going to miss some perfectly visible targets. Limits on our own introspection make this surprising to us, right? We think, I've looked at that image, how could I possibly not see that? And Daniel mentioned the medical legal side of things at the outset. This is a real problem, at least in the US, when you end up in court, because when the lawyer points to that clearly retrospectively visible cancer and says, how could a competent radiologist have missed that? Well, this is the answer to how a competent radiologist could miss that, but it's not something that's understood well in malpractice realms. But before you go home depressed for Christmas, this GIST business shows that you have unanticipated skills to go along with these limitations. So thank you very much. That's my email up on the screen. More than happy to be in touch with anybody with questions. I think we have some time now for a few questions, and if you don't get your question answered, just drop me an email. And did you see the gorilla?
Thank you so much, Professor Wolfe. What a fantastic, entertaining, informative talk. It's been superb listening to you. I'm sure there will be some questions coming through, and in a moment I'll pass over to my colleague Ian Craven, who will manage that. But it's clear to all of us as radiologists how fundamentally important this is to what we do day in, day out. We have no training in how we look at things. Really, we have no real training in terms of what is the best strategy. Should we be drillers? Should we be scanners? But come back to the point you made towards the end about GIST. I sometimes look at other radiologists and wonder how they can look at 300 slices in a minute and understand fully what is on the scan. And you've gone a long way to explaining why that might be. I guess also I love your term about the human search engine. It unfortunately reinforces my feeling of how fallible we are as radiologists, and makes me wonder when AI is going to come into the picture rather more than it does. But I'll hand over to Ian. I think Ian.
Ian, are there?
Yes. Yeah. No. So Danny's touched on a couple of the strong themes that have come through. So lots and lots of praise for a very interesting lecture. Quite a few people saying that we should get trained on this, and it should form a sort of formal part of our training. But I suppose, do you think the evidence is currently there for us to start putting this into our training about sort of the useful ways that we can mitigate against error?
Well, so there are certainly aspects of it that that are amenable to being put into training, and some of it, at least my understanding is that some of it is there in a sort of informal kind of a way. So the extent to which you sit next to your mentor and your mentor says that the way we do you know, an abdominal CT is you have a checklist in your mind and you do boom, 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 boom. That kind of checklist strategy is an explicit defense against these, against a class of these sorts of errors. So there are these things that have developed sort of, you know, heuristically in the field that are based on perception. The difficulty is that to go beyond that, you need more data on what really, really works. And the field, the medical image perception field, is small enough that it's hard. It would be hard to be prescriptive at this point. And there are a number of interesting problems there. I've alluded to the problem of just getting enough data, but there's also the problem of getting gold standard truth out. So clearly you should do, we should be figuring out what the really best radiologists do. How do we know who the best radiologists are? Don't have those data. In part, we don't have those data because people don't really like sharing the error data. And in part, we don't have those data because we don't know about all sorts of errors, particularly false negative errors where the patient goes off without a positive diagnosis, and you don't, you know, the feedback that you missed something basically never comes back. So it's a difficult problem, but yes, absolutely. We think that in the long term, educating radiologists about how their search engine works will be useful.
There's lots of questions about the sort of the link between fatigue and workload.
Yeah,
sort of a problem that we're faced with as sort of managers and numbers crunching. What evidence is there that that plays a role in missing?
Well, so there's modest amounts of evidence in medical image perception and buckets of evidence elsewhere that fatigue does nothing good for you, time on task does nothing good for you, and that working at adverse circadian phase does nothing good for you. And I'm sure it's the same in the US, in the UK as it is in the US. You know, every radiology department I know at the moment is concerned about burnout. The sheer quantities of, you know, each time somebody develops a cool new technology, you know, great, you've gone from 2 images in this study to now there's 600 or something, and without having added any time to the day. One of the interesting bits of the sort of sociology of science of these tasks is that you know, at the airport, there's the folks who are scanning your carry-on baggage, and there are all these other people around the checkpoint, and they're being, depending on what country you're in, they're being rotated around every 20 or 30 minutes, because those guys know that if you sit there and look at bags for more than 20 or 30 minutes, performance starts to trail off. Radiologists, on the other hand, are perfectly happy. Well, I don't know if they're happy. They're perfectly willing to read for 8 hours straight or whatever, and with with the added wrinkle that they're perfectly happy to try to do this while the phone is ringing off the hook and somebody is poking their shoulder saying, will you look at this image for me? So fatigue, vigilance problems, and interruption are all absolutely not helping. Again, typically, at least from what I know in the US, those factors are not being handled terribly well in your average radiology suite.
So there's sort of a question leading on from that, and it's a sort of threefold question. Firstly, should we be screening in recruiting into radiology? Should we be screening for people who've got, you know, perhaps excellent sort of visual spatial awareness or skills? Is there any evidence that once we're trained as radiologists and people who report images, we all like to think that we are experts in that? And is there any evidence to say that we are any better than when you do your experiments with other people who are not sort of clinically trained in that aspect? And then the final part of that question is, where does AI fit into that? Because lots of us are sort of particularly worried about AI coming in and taking over all of this, and lots of people have written in the comments box that they're thinking of taking on other degrees and finding other professions fairly soon.
Okay, so for the first piece, the entry piece, it is a goal of basically any expert community I've ever worked with is to come up with the test at the beginning that would say whether or not you'd be a good expert. So let's say a good radiologist. In radiology, there is no such perceptual test at the present time. And the barriers to reaching such a test, you can imagine, are quite huge. First of all, you'd need to figure out what the what are the perceptual / cognitive capabilities that make a really good radiologist a really good radiologist. Okay, that gets us back to the problem that we don't really know who a really good radiologist is except by reputation. We don't really have gold standard data on that. Then there is it seems to me, at least at the present, a spectacular medical legal issue here that how are you going to validate that test in a way that allows me to look an aspiring, Harriet Joy in the eye and say, the test says that you're not fit to be a radiologist? Well, at least in the US, she'd be in court and nothing flat. And it would be more or less indefensible at the present time. Second part of the question, are you experts? Absolutely. There's no doubt that for any of these tasks that you're trained on, you can do things that that novices totally cannot do. And it's it's sort of vaguely akin to the wine tasting business. You can describe differences in an image that we don't even think we can see. Though if we were trained, I mean, it's not that you're seeing something that was invisible, but you have learned to see something that we have never, we novices have never noticed. There is very little or maybe no good evidence that your training produced a generalized skill that makes you better at spatial reasoning or finding doing jigsaw puzzles or any of those. You may like doing them more. I mean, there may be a sort of a matching between things that you enjoy doing professionally and things that you do in the outside world, but there's no good evidence for a special generalized talent. There's my favorite study of this is I'm afraid a sort of a US specific study. There was in the New York Times on Sundays, there was a cartoonist who would draw these beautiful pen and ink line drawings of whatever the latest show opening on Broadway was. And his daughter was named Nina. And in these very elaborate drawings, he would hide the name Nina. These were called Nina games, and a great important part of my youth was playing the Nina game every Sunday. And one of my colleagues went and got a population of radiologists to see, are they any better at doing this kind of a task? And sadly, the answer was no. They might enjoy it. It might be part of what they think is fun, but no special ability. All right, now, how about AI? Is AI gonna save us all, or throw you all out of a job or whatever? I think that the shorthand answer, I'm not a great expert here, but I think the shorthand answer is that it will not in any way eliminate the role of radiologists. It will change it in much the same way that machines changed, looking at blood samples. Once upon a time, somebody must have been going through and laboriously counting all the red blood cells, and now you just stick it in the machine. There will be routine tasks like that that you probably won't miss, that will get offloaded to machines in the foreseeable future. But the what does it mean part of radiology, I don't think anybody's got a claim that AI is going to do that anytime soon. From the vantage point of the stuff I was talking about today, the really interesting problem is what we do until, if and until the AI becomes perfect in some realm. If in mammo at this point, a good AI is basically as good as a good radiologist, which is great, but not good enough to leave them on their own. So you're still going to need a human in the loop, and that poses a really interesting problem. So let's suppose you've got an AI that will find 95% of cancers and will produce a false alarm on 10% of cases. That would be comparable to a very fine radiologist. There are machines that do that. That's great. Now let's think about deploying this in the field. You got, let's say, 1,000 images in a screening situation. There'll be 3 or 4 cancers in there. Let's give the radiologist, let's give the AI full marks. It gets all of them, and it produces false positive marks on 10% of cases. So it found 3 or 4 cancers, and it made a false positive marking on 100 cases. It delivered that to the radiologist, who still has to be in the loop. The positive predictive value of any mark is about 3%. And if I give you advice that's good 3% of the time on restaurants or movies or whatever, you are not that interested in my opinion. And this has been, this appears to be a serious problem for AI deployed in the field in this particular kind of screening situation, which is that the radiologist comes to the conclusion that the AI is useless. It's finding things that most of the time the radiologist would have found, and it's telling you about things that the rest of the time are clearly turn out to be false positives. What do I need this thing for? Except that in the US, I get paid $5 extra if I push this button. So I think I would say you don't need to immediately retrain. I'm not sure that I would encourage somebody just starting to decide that they were going to devote their entire career to doing just screening mammo or something. Those are the sorts of tasks that AI will get good at. But it'll be a while before the mammo robot is doing the interventional stuff, let alone just talking to the patient.
There's one other question, but I also want to point out in the chat box that we've posted a link for CPD certificates and for feedback. And I know there's over 200 feedback forms already been completed. So it's obviously, we're going to get some good feedback. But there's also a link been posted for your website for people who want to volunteer for these sort of experiments. We'll also be sending out an email to everybody who's attended and registered, so that you'll get all this, the links sent to the email that you registered for the talk, so you'll get those as well. But the final question I wanted to ask, which again has come through quite a lot, is when we're faced with the medical legal world looking at our work and a judge or a barrister sort of showing something that we've missed in black and white, and obviously retrospectively it's very easy to see something that wasn't visible in inverted commas at the time, are a lot of these sort of perceptual problems and patterns of awareness that you're talking about, are they understood by the medical legal world as mitigating circumstances for us, or are they something that we should be educated in to sort of try and bring up when faced with those sort of questions?
My impression is that the penetration of this kind of information into the medical legal world is pretty minimal, and I don't know my way around the British system at all, but here certainly I think that part of the answer would be that when you are unfortunately defending against a case that has to do with a clearly retrospectively visible finding, that it would actually be useful to get somebody like me or your lawyer who took the course in college or whatever, to show the jury one or more of the kinds of demos that I showed today, not the radiology ones, the Giotto style ones, because I think there's nothing like showing that it is perfectly possible to have something that any idiot can see not be seen. I think that would go a long way to explaining. I mean, we can explain it all in very nice, highfalutin theoretical language about the costs of uncertainty and things like that. But I think that those sort of demos would be extremely informative to a jury of your peers. But to my knowledge, there's very the one time it wasn't actually a radiology case, it's a driving case, but the one time I actually got close to being on the stand for this purpose, I got thrown off when the judge declared that everything I knew was common knowledge, and you can't be an expert if what you know is common knowledge. But that's a story for another day. So hope that was useful, and if there's anybody in medical legal land out listening today, I'd be very interested to hear how this plays out in the UK setting.
That's great, thanks. I think that's all the questions, or I've tried to sum up. There are lots more questions out there, but I've tried to sum up the main topics. So I apologise if your specific question has not been asked, but I think we're drawing close to time, and I know Danny wants to say a few more words.
Thank you, Ian, and more importantly, thank you, Professor Wolfe, for again a wonderful lecture. I'm sure we found it all very enlightening indeed. I'd also like to say thank you to Ian and colleagues on the Training and Education Subcommittee, who you'll be able to see as panelists this evening. Without their support, this sort of event would not be possible. Thank you to the Royal College and to colleagues in other specialty imaging groups for having spread the word about this. This is fundamentally important, and I'd encourage all of you to read the emails that will come through tomorrow from us, and to respond to Professor Wolfe's invitation to get involved with his studies. Before we close, it's a tradition within the BSNR to award a medal to our main speaker of the year. That is yourself, Professor Wolfe. The medal is the James Bull medal. James Bull was one of the fathers of neuroradiology. He was based at Atkinson Morley Hospital in the 60s and 70s, and every year we award the James Bull medal. So we'll be awarding that to you, Professor Wolfe. It's not a virtual medal. It will get sent to you physically. And also we would naturally like to award you honorary fellowship of the British Society of Neuroradiology, and thank you. So once more, on behalf of everybody, and there's been an enormous number of comments coming through in the chat saying the same thing. Thank you very much, Professor Wolfe, for what has been a wonderful evening, and one that will live in the memory for a long time.
My pleasure. Thank you.
And thank you to everybody for attending, and good evening, and have a great Christmas.